All right. So it's great to see you guys. I am happy to be able to help you guys learn machine learning. So I did want to make a couple announcements today. I was asked by someone from another company, and then my company will be looking as well. So I have started as a director at Merits, and we're going to be putting some junior level data scientists on staff pretty soon. We've also got a senior analyst, which is more of a data strategist, open. So I wanted to let you guys know that. I also have been working really closely with Databricks. As you know, I teach a PySpark class. They are looking for solution architects in St. Louis and throughout the country. So if you guys are interested, please feel free to shoot me an email. It's kelsey.mnet@gmail.com. Just wanted to let you guys know in case you're looking for any opportunities. All right. So today I'm going to be going over ridge regression, lasso regression, and we'll be doing a review of linear and logistic regression. In general, when you take statistics, they will use the maximum likelihood method for linear and logistic regression. I'm going to show you something a bit different. In general, when you use it for machine learning, they use something called gradient descent. And that same concept is very, very important for neural networks. So I think doing it that way and teaching it that way would be the most helpful. So I'm going to go through the slides, talk a little bit about it, and actually show basically the linear and logistic regression, tweaking a little some things and showing you the difference between the different methods. Most of you hopefully have been on here before, but if not, I am using the treatment episode dataset, which looks at whether a substance abuse treatment is a first admission or a repeat admission. So that's what I'll be working with today. It's a larger data set, so there is a smaller data file in there that you can feed into about halfway down in the code, so you don't have to do all the data munging. I chose randomly 200,000 rows. So first I'm going to start with a linear regression overview, then I'm going to talk about logistic regression, and then I'm going to move on to what I really want to teach about is ridge and lasso regression. I'm assuming some of you probably have some linear and logistic regression experience because it's taught in a lot of statistics classes. So I'm not going to go over it in great detail. So linear regression helps you predict a continuous or a numeric value. In general, the way that I tend to explain it to stakeholders, you can almost think of it as a weighted average. So if you're looking at the formula here, you'll see a couple different things. I am going to try to use some of the different symbols, because if you ever go in and read a machine learning book and you don't know those symbols, it can become pretty difficult. So you've probably seen this in high school algebra as y equals mx plus b. It's the same thing, but it's expressed a little differently. So here we have our predicted y value. If you see a caret, it's always a predicted value. If you see it without a caret, that means your actual y value. And we are trying to predict that y value. And on this side, we have a y-intercept, which is here, our intercept. And then we have, based on how many factors go into our model, we have an x and then a coefficient associated with them. A coefficient is similar to a weight. The model takes your data and tries to pick the best coefficient that allows you to draw a straight line and predict that numeric value that you have. In general, if you see that n, it's going to be the number of features in our data set. So you can see here, it starts off with 1 with a subscript. It has 3 dots, and then you can see it goes up to n. you're going to see that when we're talking about how many features are in our data set. So if it goes from 1 to infinity, instead of writing them all out, they're going to do 1 to n. And then you also see the xi. You'll see that it's not up here, but you'll see that frequently. The I is the ith feature, or very similar to n, off into the future. And then I don't even know what this is called, but 0 with the line in the middle is it talking about the different parameters in your model. So those are the things that the model sets. You can see one here as the y-intercept, and the coefficients are here. So an example down here would be predicting a housing price with 2 features. So we would have our y-intercept, our coefficient times whatever the square meters are, plus our coefficient times the number of bedrooms. This would probably not be the most accurate model in the world, because the housing price has a lot more than just these 2 involved. But I did want to show a simple example of what that would look like. Are there any questions? Awesome. So in general, you're going to see this not just in linear regression. You're going to see this in every machine learning model you'll do that is trying to pick a numeric value. So you're going to see the mean squared error, root mean squared error, and mean absolute error. They're very common cost functions, or basically how we predict how our model is optimized, like what function is used to make it the best model that it can be, as well as when the model is done being trained, it will spit out a mean squared error, root mean squared error. And then we can do that for every model that we try in our experiments. And then we can compare them. So in these cases, we want the values to be smaller. The smaller they are, the better the model is. So the one that you're going to see most often is probably root mean squared error. So that takes our predicted y value minus our the actual y value. We're squaring that and then putting it over n. And then we're doing a full sum of all of those squared errors, you could call them, and then finding the square root. The reason that you would want to use the root mean squared error above other metrics, say, because we are doing this squared, and you're going to see it up here too, that makes it so that when you get large outliers wrong, it actually penalizes the model a lot more than it would if you were using a mean absolute error. So this squared makes it so if we're really missing a lot, our root mean squared error or our mean squared error are going to shoot up. These are the same thing, just one of them is under a square root, so it can look more like the values that are coming in and more like those predicted values. Mean squared error is not going to really look like those predicted values, so the error won't make quite as much sense. Mean absolute error doesn't find the square root. So we have our predicted value and our actual values. And we're taking our actual minus our predicted values, finding the absolute value, and doing a sum, as well as multiplying it by 1 over the number of features in your data set. This, on the other hand, like it doesn't have a squared, so there will be much less penalty for outliers when you use the mean absolute error. So you would want to, based on your use case, pick which one is better for you. So are outliers really not that important for your use case? Do you not really need to predict those outliers? If you don't predict those outliers, is your model going to be worse off? If that is the case, if they're not important, you would maybe want to use the mean absolute error. But say you're trying to predict something that has costs associated with it. And if there's one value that you get really, really wrong, the cost associated with that prediction and getting it wrong would be large costs. If that's the case, you would definitely want to use either the mean squared error or the root mean squared error, because it would really penalize those outliers more than when you're just getting it wrong a little bit. So that is an example of something that you would need to know and understand the business use case in order to choose the right method for the machine learning. And you do that by asking questions. Are outliers important? And bringing them up with stakeholders. So the reason I try not to go into presentation mode is because I'm going to be flipping between code. But I do want to show this in a zoomed in fashion. So what I'm showing here is something called gradient descent. I've already mentioned that this is used in neural networks as well, and it might be a different flavor from what the linear regression that you've been taught in statistics classes. There's multiple ways to optimize our linear regression, and gradient descent is one of those options. You probably have looked at the likelihood estimate and have seen that in the past as well. If you want a review more on that flavor of things, there is a slideshow in my statistics and R class. Feel free to take a look at that, and I go over that one in much more detail. But since you're here for machine learning, I want to talk about the one that's going to help you more as a data scientist. So usually when you have a machine learning model, there's usually something that's randomly initialized. That is the case here. So we start off and the model will randomly choose a coefficient or our weight values. That's the same thing we were talking about. So it starts off, randomly chooses them, and then it tries to make a prediction for every one of its data points when it has those randomly initialized coefficients. It then compares the predicted and the actual values with these cost functions that we just talked about. So it uses one of these, whichever one you specify. And it spits out, say, a root mean squared error. And then you actually use a little bit of calculus. I'm not going to get into what a derivative is. I want you guys to get enough knowledge that you could go and dig into that on your own. But you will have something that looks like this. Each one of these dots is an iteration. So I've run this model multiple times until we get to the optimal value. Our randomly initialized values are this orange one. This is the random one. So we then have our cost function. We find a derivative, which is basically finding the line that is tangent to a curve. We use that sign of the derivative. So basically, if our curve is like this, our derivative is going to be going up and down like this. We know that if we go down our cost function, if that sign indicates downwards, that our values or our predicted values are going to get better. You can almost think of it as an instantaneous rate of change. So we're finding on that point in the curve, is the curve going up or is it going down? And based on that sign of the derivative, a positive or negative, it will move a little bit farther down that curve, and then it will run the model again with those new weights involved. And then it will keep doing that until it hits an optimal value, where if it actually tries to model it one more time, it ends up going up the other side of the curve. And then we know that we hit the bottom value. So you'll see something in a lot of machine learning models called the number of estimators. That this is what that is going to refer to. So how many times do we want to run the model to actually go through this process? So once we hit that bottom of the curve, we'll know what coefficients are associated with them, and we will have something that looks like this. Our top graph shows our actual values in red, and then our predicted values are on the blue line. So the lines connecting those red dots and the blue lines are our error, and that's what would go into the cost function. So every time you use a linear or logistic regression, it is going to be a straight line. If you want something that is not for linear data, you will have to move on to a machine learning algorithm. Are there any questions about this? All right. So this was talking about linear regression. And actually I should stop here and go a little bit farther in. So I said that every model has a straight line involved in it, and we've iterated through multiple models. That shows shown here is what those lines would look like, and then our data below it. This green one here will be the optimal fit, and then the other ones that we've tried will be these red ones, and then we end up with our y-intercept, our slope, and whatever feature it is. This would be feature number 1 in our model. So logistic regression, the difference between linear and logistic regression is predicting a category instead of linear regressions predicting a numeric value. So that logistic regression will be, in some cases, predicting a yes, no. We call that a binary. So is it present? Is it not? So 2 categories. There's also something called multinomial classification, which allows you to predict a target with 3 or more features. So if you were looking at a high, medium, low, or something that had 4 or 5 categories, that would be a multinomial classification problem. So no matter what model that you use, it will return a probability between 0 and 1. So that probability we will then turn into a prediction. You usually set a cut point, and that cut point in a lot of cases, the default is 0.5. So if it's 0.5 or above, it'll round that prediction up and give you a 1. And if you have something below 0.5, it will round down and have a prediction of 0. You, as the data scientist, can try multiple cutoffs. So say when you're doing your model, I often find that it's missing on one side a lot more than it tends to miss on the other side. So we talked about precision and recall last week. So in general, usually I find the precision is really good the whole time and the recall is bad, or vice versa. And changing this cut point would help you actually find that optimal mix between the two, because you're always going to see a trade-off between precision and recall. Think false positives and false negatives. So this cutoff, as we said, can be adjusted, and we saw the ROC curve last week, which looks at how often you're getting the false positives and false negatives and finding that optimal value. So what's the difference between linear and logistic regression math-wise? We've talked about how one is a category and predicting a category, one's predicting a continuous value. So actually, logistic regression is very similar to linear regression when you do it with the gradient descent. So just as we talked about in linear regression, it fits your data to a straight line. In logistic regression, it's a bit different. It fits your data to an S-shaped curve, which is called a sigmoid function, which is another one you're going to hear a lot in neural networks and deep learning. The sigmoid function looks something like it's shown in the bottom right-hand corner, this S curve here. So, for instance, these red values up here will be those ones that were predicted. And then these down here would be the zeros that were predicted. And it would be closer to a straight line in between. And then after you have fit it to an S-shaped curve, there's an added step of finding a weighted sum of our input features, just like when we did in linear regression. But instead, because it's on this sigmoid function, it's actually set between 0 and 1 instead of a continuous like line between two values. So basically, in order to get it and take those values and make sure that it's between 0 and 1, we take whatever equation comes out of that linear regression, which you can see in number 1 up here, and we put it in that sigmoid function. So where this x is, the e to the negative x, we actually put that function in there, and that fits it to the S curve with 1 above and 0 below. Are there any questions about that?
Yeah, two quick ones. One, with the cutoff function, is that just a single value, or could it be like 0.7 and -3, or -0.3, sorry, and positive 0.7?
So if you're doing multinomial logistic regression, you could have multiple cut points because you're, say, predicting 3 values. If you're only predicting a binary, there would only be 1 cutoff. So say if it's above 0.7, it would be a 1. And if it's below 0.7, it would be a 0.
Okay.
So it depends on how many features you have, or how many categories you're trying to predict.
Yeah, so 1 per variable, basically. Yeah. And then, so would it be accurate to say that you basically perform linear regression as a first step to logistic regression?
Yes. And then you're actually putting that into the sigmoid function. Exactly. It's exactly right.
Thank you.
Are there any other questions? All right. So in reality, I usually don't use linear and logistic regression a lot. However, I use a variety of linear and logistic regression all the time. So there's something called regularized regression, and you can do this with predicting numeric or predicting categorical values. So in general, in machine learning, we do something called feature selection. So we're taking, and we usually throw in the kitchen sink the first time around. We throw in all of our features that are in our data set or subset, and we try different ones. And then we do something called feature selection, trying to calculate the most important features. And by features, I mean the dependent variables or the variables that you're using to predict your predicted or target value. So in general, data scientists refer to dependent variables or variables as features. So those features, we have to, we discussed overfitting the last time. So last class, I talked about how if you have too many features, usually you can have more if you have more data. But say you only have 5,000 data points and you've got 30 features. That's going to do something called overfitting. So it's going to take that data and more or less memorize your training data, and then it will not generalize well to new data coming in because it will be too tailored to your training data that you're using to make the model. So regularized regression is really good because it decreases overfitting. And it lessens the assumptions of linear and logistic regression. In general, there are a list of 4 or 5 assumptions that have to be met in order to perform logistic regression and not get unbiased estimates. I'm not going to go over them in detail, but they are in the appendix of these slides, and I also did a class on them in my statistics in R. You can get away with doing a lot more with regularized regression because it takes away that overfitting aspect of things. It also allows you to do feature selection very effectively. So I'm going to be doing a whole class on feature selection, but the ideal way to do feature selection is to run every single model with all the features in, and then you take one out and see what happens when you take that feature out and take the next feature out and take the next feature out. That would be ideal to do it that way, but that's a lot of processing power. So if you have big data and you taking them in and out and rerunning your model thousands of times, potentially, if you have a lot of features, it's just not going to be something that's feasible for you as a data scientist. It's going to take too long. So my method that I use is I use 4 different models usually that help gauge feature selection. They're all calculated slightly differently. So I then take the results of those 4 different models and see which features are showing up over and over again at the top of those models. And then I choose them for my features. That way we're kind of circling around and doing feature selection in multiple ways. Regularized regression comes in there because I like to use Lasso in particular, Lasso regression and Ridge regression to do feature selection. That will make more sense in a bit. I'm going to go over in the next 1 or 2 classes what I use, the other 2 models that I use, which are actually better than these. But regularized regression allows you to actually change the weights of your coefficients in order to penalize those variables that are unimportant or they're not showing up as important in your model. So they'll actually, in some cases, either be decreased in their importance or be dropped out completely. That varies based on if you're using lasso regression, ridge regression, or elastic net regression. So now, after I explain this, I'm going to jump to the code and do a live demo of this. But ridge regression is something, and both Lasso and Ridge do this part of it. They add a penalty term that penalizes the size of your coefficients or those weight values. So it reduces those coefficients towards 0, and the ones that are really unimportant get a lot smaller than the ones that are important. So it decreases bias and overfitting in your data. And it makes it so that those small coefficients really aren't affecting your predictions very much. They're having very little weight involved in them when making those predictions. That's something that you can vary. It's usually called a regularization parameter. It's often called C. And at 1 will be normal linear regression or logistic regression that we just saw. And then the lower that you make it, the more the penalty shows up on your coefficients. I'm going to show this in actual code from the notebook for this class. But you can see here, I have a ton of features, kitchen sink, threw everything in. This is not the right way to run a logistic regression. But for example's sake, I wanted to show this to you guys. So this is the normal linear regression. We've got our different weights here. And you can see the ones in the middle there's quite a few in the middle that aren't very important. Now, if we take that C, decrease it to 0.2, we're seeing that the middle there, in this case, there we go. Sorry, accidentally clicked. In the middle, these values are made smaller than up here. It's very subtle though, and you can see that these weights have also been decreased somewhat. However, when you go to 0.001 for your C value, we can see a big difference here. The really important ones are still standing out, but those ones in the middle are going down to almost 0, and their weights and their coefficients are really, really small. So I'm going to now go into a little bit of a demo about this, show how to do this in scikit-learn. and kind of talk to you about how I would maybe decide which ones were important and which ones were not. So I'm going to come up all the way to the top here. So this is where you can feed in the smaller data set halfway through the code if you don't want to go through and run the cleaning on the much larger data set. You actually get pretty similar results from doing both methods. It won't be quite as good with all the data. So in previous classes, we've gone over how to set up our model for machine learning. So I'm not going to go over this today. And we've also gone over something called confusion matrices. So we'll see that. And we're going to see the ROC curve come up as well. So once we're here, we're already have our values for this logistic regression predicting our first admission or repeat admission. We've already got it put into a training data set, a validation data set, and a holdout data set. So we're going to be using our training and our validation here. So we take, we're going to use all of the standard logistic regression inputs for this model. We're not changing anything. We then put it through and we fit our model to our training data. So we're going through that process of gradient descent, randomly initializing our coefficients, adjusting it a little bit more and a little bit more until we get to our optimum value. So we've gone through that process, and then we actually take our smaller chunk of our data set, the prediction data set, and we go in and test how accurate our model is with that unseen data. So we took everything. You would have parameters here if you were changing them. But in this case, we're using the defaults. I do want to show. So I, in general, really like the scikit-learn documentation. I find that it's really useful, especially when we get into the more complex models. It helps to be able to look at these different parameters and remind yourself what they mean. And they actually give a definition for these for the most part. Really high level, but it's helpful. So we have our penalty. We talked about ridge regression. So ridge regression is like the L1. Lasso is L2. Elastic net is somewhere in between. But you can see here, we talked about C. That's here. It says the inverse of the regularization strength must be positive. So you could go through and look at these different values and know more about what they are. So I highly recommend using it pretty frequently. So we've trained our model. We're looking at our model accuracy now. I created a little function that would create a confusion matrix. I'm also pulling out our precision and our recall. Remember that I said in general, usually a model predicts one side badly and the other side pretty well. That's showing up here. So in this case, we are getting our zeros wrong. We are the people who are on their first admission. So we're predicting in a lot of cases, so it's often easier to see this in the confusion matrix. So we're getting 2 or more right a lot. But for our first admission, our true label's here. Our predicted label is here. We're often predicting the first admissions, and we're saying or predicting that they're actually second admissions. So we're getting those first admission people wrong a lot. And you're going to see that trend as we go down. It's always going to be that one that we get wrong. The other one does a lot better, the other side. So that is a case where you'd want to play with the cutoffs. I'm not going to do that today, but that's definitely a use case and a red flag that says you need to adjust these. So the next thing that I'm going to show here, unfortunately, when you print this, you can't get like the middle. So I'm going to break it down in a minute. But you can see the coefficients here I ordered them in decreasing order, so descending order. And you can see in this case, which is actually very interesting, the one that's floating to the top here is the race of Alaska Native. In general, if you've read the literature on substance abuse, that's not super surprising. There's also, and this coefficient shows us that as the percentage of this race goes up, so does the likelihood of a repeat admission. We're seeing that being in the mountain division, I believe those are census divisions, that is also associated with increased risk of being a first admission. So now we're looking down here. We're seeing that these are negative, so that's an indirect relationship. So that means as these values are going up or more people are associated with these, they're less likely to be a repeat admission and more likely to be a first admission. So we're seeing if somebody lives in a U.S. territory instead of a state, the division of the Pacific, if they're on a stimulant when they come into the clinic, they're less likely to have been a repeat admission and more likely to have been a first admission. So here I'm going to show, I actually find the mean of the coefficients, not really because this means anything practically, but I want to show you how as we change that regularization parameter, the mean of our coefficients is going to drop. That's the only reason I'm showing that, just so you can see that the coefficients are reducing. And then we have the plot that I just showed you, looking at the different coefficients here. Are there any questions? All right. So we went with the default. So we have one, it's just normal logistic regression when we're doing this. So our model is definitely overfitting. So now we're going to go towards a ridge regression, which is the L2 regression here. We both say that we want to use ridge regression. So the penalty will be L2, saying we want to penalize those high coefficients. And we're also changing the C value or the regularization parameter. In this case, you can see in the markdown, and I do, if you want to go through this another time, there's some explanations put in here as well. So when that C is 0.2, it looks a bit different. So we're going down. Our accuracy actually didn't change. A lot of things didn't change. And our coefficients are slightly lower. So moving to 0.2 didn't do a whole lot. We're still seeing that those same values are coming to the top here. Now we're going to do one better and change it to the 0.001. Now we're increasing that penalty. And now we can see that our coefficients, they were, I believe, the mean was, and I'm losing it there, 0.043. So if we go down here, we're seeing our coefficient mean is 0.02. So it's much smaller. We are seeing that it looks a bit different here. So when we've taken out those variables that were overfitting, possibly overfitting, these shifted. Now the division, mountain division is coming to the top. So if you're in the mountain census division, you're more likely to be a repeat admission. The west, north, central in the country, more likely to have a repeat admission. Again, Pacific is still showing up as the highest negative correlation, and then the division of South Atlantic is showing up as well. Interestingly, if you had brought in by an ambulance or ambulatory in an ER, it's more likely your first admission to substance abuse treatment. So one thing that I didn't even notice the first time I went through that is interesting. So when we looked at these, US territories are a very small portion of the data. Same thing, the race Alaska Native is in general a very small percentage of the population. So when we actually penalize those high coefficients, those two small groups dropped off completely and they were removed. So these were in here as probably a false flag that it was being caused by overfitting. Didn't notice that the first time through, but it's interesting. Are there any questions about that? All right. I'm going to quickly go back into my slides. And so we've been talking about ridge regression, L2 regression. I always get L2, L1 mixed up, but ridge is L2, lasso is L1. Lasso regression is a bit different because it adds the penalty term a little differently. In ridge regression, the middle values are never zero. They get really close to zero when things aren't important, but they never hit zero. Lasso regression allows the penalties to actually drop down to zero. So if it's unimportant, they're going to disappear from your model altogether. So you're going to see as you take that regularization parameter going from c equals 1 to 0.2 to 0.001, this looks a lot different now. Like we only have a couple features left at 0.001. More are completely dropped off at 0.2. And so we can see a very big difference from if we go back to ridge regression here. So our end model looks very different. So that C parameter works in the same way, but it can hit zero. In Lasso, it cannot in ridge. So why would you want to use one over the other? Both address overfitting, so they both do the same thing or are used for the same purpose. It helps with the handling of multicollinearity. One of the assumptions that I talked about for linear or logistic regression are that your features or your dependent variables are not highly correlated with one another. So basically, if you use ridge or lasso regression, the ridge regression, if you have two highly correlated features, the coefficients of the correlated features are actually going to look similar. If you have lasso, it will keep the one that has the higher coefficient and it'll drop the other one completely from your model. So with that, lasso is better when you have a few important features, and ridge is better when there are many features that have importance. Why is that? In general, there's a much more information lost when you use lasso regression. So machine learning in general is good at picking up small patterns in your data, even that aren't showing up as super important, but actually using them to influence your predictions so you can take into account a lot of different factors at the same time. So Lasso completely removes them from your model, and you lose a lot of information. But if you have highly correlated features, maybe that's helpful. So Lasso is also better for performing feature selection. It's unambiguous. If it goes to zero, take it out of your model. If it isn't zero, then maybe it stays in. Ridge regression, you have to kind of decide based on more like gut, where to put that cut point and how big should the coefficients be to keep in or out. So Lasso is pretty obvious. You also have elastic net, which I haven't talked about, but it's basically it's the best of Lasso, the best of Ridge, and it's somewhere in the middle of those two. So feel free to look that up if you want to learn more there. Are there any questions?
I have a question.
Mm-hmm.
So is it always the case that ridge regression is going to have a better fit for the overall model compared to Lasso?
So no, it won't. It'll depend on your data. So that's the last two bullet points here are very important. So say you're trying to predict something and one or two features completely dominate. I'm actually working on something at work right now where there's a couple projects I'm doing, and there are two features that are explain 75% of the variance together, or even maybe more than that. And then the rest are really, they have some significance, but they're not that important. It's overwhelmingly two features. So Lasso would be better for in that circumstance because you're not really losing a lot of information when things drop to zero if the things in the middle aren't important anyway. Ridge would be better if there are many features that all give valuable information and that are all important. So that would be the case there because you're not losing the information of those ones that are less important in the middle.
So follow up, does it make sense perhaps to do a data reduction PCA prior to ridge regression?
So that is something that you will probably do a lot. And it's something in general, I tend to do that as a default in some cases. So say I actually did it in this model. I had 3 geographic variables that obviously are going to be really highly correlated with one another because they're nested within each other. But like city was in one of them, and I probably wouldn't have been able to throw it in my model as is because there were too many variables. So I actually took those 3 categories and used PCA on them. For those that don't know what that is, it's principal component analysis or dimensionality reduction. So basically taking the most important information from those features, putting it in a smaller number of features and getting rid of the stuff that's the same across all the features. So PCA is always a good thing to try. And that often makes your model better. PCA is more important we talked about k-nearest neighbors. K-nearest neighbors is terrible with a lot of highly correlated features. So that would be even more important in the k-means model. There are any other questions? I can go in and show a little bit more about Lasso, how it's done. All right. Just look. So going back into here, now we have our Lasso regression. So we're going to start off with that 0.2. It's just the one that I wanted to show. We have L1 penalty here now, and we're putting that C value as 0.2. That's the only thing we're changing. It looks exactly the same other than that. In this case, again, our accuracy is looking similar across those different ones. So as we've tuned this, it hasn't changed much. That tells me that our data probably isn't linear. So it's not getting much better as we're changing it. This might not be the best model for us. And then we're looking, this looks very similar. We're getting the first admissions wrong. We're getting the repeat admissions right. And now with the 0.2, we're going to see, even just with the 0.2, our coefficient mean is way smaller than 0.2 with then it was 0.043 with ridge regression when we changed the C or penalty parameter to 0.2. So this is a much smaller number for Lasso because it puts so many in the middle as 0. And that hopefully I can show. Okay, so we would want 0 through 20. Did that the wrong way. Here we go. So we're seeing here, if we actually look at the coefficients themselves, they're dropping off And if we, hopefully it won't cut it off if I do this. They're going down to 0 here. So in the middle, we would see that there are probably a lot more zeros, and then they're going to go up the other side as well. But you can see these are zeros. Up in ridge regression, they would be very small, but they wouldn't be 0. And then I show our model coefficients. We've seen that in the slide already. Now we go down to 0.001. We changed our C value. Our model got worse when we did this because it took out a lot of the information that was useful. So our accuracy actually dipped, and our recall, basically getting these first admissions right, is really bad now. So our model got substantially worse. We lost too much information. So here we can see 0 through 30. We can see that it's we've only got like 8 or so features before it drops to 0. So it took almost everything out of our model. So that's why our model got really bad. But if we go up to ridge, going to do that same showing of the coefficients. And 0 to 30. They're small, but they aren't 0. So that's the difference between all of those. And finally, if we talked about the rock curves and the different cut points, I took every model that we created and did a rock curve to look, and this takes false positives and false negatives, basically how many times you're getting the positives right, how many you're getting the negatives right. And they look really similar. So basically having a larger area under this curve is best. This shows that in general, maybe a different cut point might be better. We would want to try something on a different area of this rock curve. We've been using right on the 0.5, and this would change based on that cut point, and we'd go up and down that curve. But most of our models are the same, except for I think that last one is the green one. It was quite a bit worse. Let's see if there's any questions in the chat. Does Baruta package do something similar, eliminate non-significant variables? I've never heard of Baruta. I'm not sure. I can't answer that one. Kelsey, please could you repeat the relation with the correlation value and your thought about the most negative correlation value feature? I'm not, Christian, I'm not 100% sure if you could unmute and explain if you would still want to answer that question. We didn't use correlation. Maybe coefficients is what you meant?
Hi, Kelsey. Yes, please. You said something when you show the most negative value on graph. You mentioned something about that feature.
This one?
I guess the most negative. The last one.
Okay, so this one, let me get rid of this again. There. I think this is what you're talking about.
Oh, it's not refreshing my screen.
Okay, so
yes.
let me yeah. Okay.
Probably. That was prior to regularization. I guess was division territories.
Yeah.
But you say something like I don't remember the
yep, I got it.
The
I
words
can answer your
you
question
said,
now.
but But it's a relation or an explanation about what means that negative value.
Yep. So I'll try to answer that real quick. I do have to get off like one minute early, but so my theory here, just having done this, we're seeing the race Alaska Native. That's going to be a very small part of the population, but the Alaska Native race tends to have, just in general, Alaska has high substance abuse problems. It's just they're known for it. But it's a very small part of the population, but they're going to have a massive amount of it compared to the other areas. The U.S. territories, I'm guessing, have less of a problem, but it's also a very small portion of the population. So when we go down here, increase the regularization, that disappeared probably because it didn't explain the effect of substance abuse readmissions in a large portion of the population. It did it pretty effectively, but for a small portion. So it ended up being less important and taken out of the model. All right, I got to jump off, guys. Thank you so much. I really appreciate it. Had fun. Hopefully you got a lot out of this. Talk to you later.
Thanks a lot.
Thanks so much.
Thanks.